All right, in this podcast, we're going to talk about isotopes. Isotopes are when you have atoms, so more than one atom. They're the same element, which means they have the same number of protons, but they have different mass numbers. Now remember that mass numbers are dependent on protons and neutrons. Well, protons tell us what the element is, and we know they have the same number of protons, so the difference has got to be the neutrons. Okay, so basically it's when you have two atoms, they are the same element, meaning they have the same number of protons, but they have different numbers of neutrons, which means they have a different mass, okay? Down below here you see carbon-12 and carbon-14. Carbon has an atomic number of 6, which means that it has 6 protons, so both carbon-12 and carbon-14 have 6 protons, but carbon-12 only has 6 neutrons, whereas carbon-14 has 8. Okay, so that's the difference between them. So they're isotopes of one another. All right, so what are the different ways that we can symbolically represent a specific isotope of an element? Okay, so specifically say how many protons and neutrons are in the nucleus of this particular atom. Well, the first way is the nuclear symbol. The nuclear symbol shows the mass number, the atomic number, and the element symbol. Okay, like here. So if it said carbon-12, 6, that means it has a mass of 12 and an atomic number of 6, and the elements. The other way to represent what specific isotope you have of an element is called hyphen notation. Hyphen notation is when you write the name of the element, so carbon, and then you put a dash or a hyphen, and then you put just the mass number. So carbon-12, this indicates to us that we have an element of carbon, which we know has an atomic number of 6, so 6 protons, and it has a mass of 12. Okay, so that's another way that we can represent. All right, now let's look at some examples. Okay, so we're given this information, and then we need to figure out all of this information and try to come up with a symbol. All right, so chlorine-37. Okay, so we know that the atomic number for chlorine is 17, and that's straight off the periodic table. And we know the mass right there is 37. Okay, so that means the number of protons we have are 17. The number of electrons, well, we aren't given a charge, so we can assume that it's neutral. So that means the number of protons and electrons are the same. And the number of neutrons is the mass number minus protons, because we know that protons plus neutrons equals mass. So if I have the mass and I have the protons, I can figure out the neutrons. It's just the difference. So 37 minus 17 is 20. Now to write the symbol, we'd have chlorine, our mass on top, and then our atomic number on bottom. Okay, like so. All right, let's look at another example. All right, this is chlorine-35. Okay, so it's still chlorine, so our atomic number is still 17, and protons and electrons are still 17 because we're neutral. Mass now, though, is 35. Okay, so then when we do our neutrons, we have 35 minus 17, which gives us 18 neutrons. So then when we write our symbol, the mass is 35, and then atomic number is still 17. So those two examples are isotopes of one another, okay? All right, now let's talk about the number on the periodic table, the mass number, which is actually not the specific mass of any isotope, but rather it is the average atomic mass of all the isotopes, okay? So basically they take all the isotopes' masses and their percentage in nature, which we call their percent abundance, and they do a little calculating and they get what's called the average atomic mass, okay? So in nature, if you were looking at a specific element, you would expect to see different amounts of each of the isotopes. So down here you see you have magnesium. Magnesium has 3 common isotopes, magnesium 24, 26, and 25. But you would see them all in different abundances or different percentages. So if you picked up one sample of magnesium from nature, like over here, you would expect the majority of them, almost 80%, would be magnesium 24 as represented by the purple, and then 11% would be magnesium 26 by the red, and then 10% would be magnesium 25, which is represented by the green. Then scientists do this lovely little calculation that I'm going to teach you how to do in a minute, and they come up with a number that's on our periodic table for magnesium, which is the average atomic mass. Okay, so it takes the mass of all the isotopes and their percentages and takes all that stuff into account. All right, well, how does the abundance of each isotope affect the average atomic mass? Okay, so here again, we have magnesium. And you see, let me change the view so we can get the bottom view as well. All right, this view is a little better because it allows us to see everything that is on this slide, okay, because this slide has a lot of information. So remember, there are 3 isotopes for magnesium, 24, 25, 26. So each one has one more neutron than the one before it, okay. Up here, there are some different percentages for the different isotopes, okay? So on this first example, the majority of the isotopes found in the sample are going to be magnesium 24 as represented by the purple, okay? And you see that the mass, the average mass, is closest to the mass for magnesium 24. So the average mass is 24.3, and that is closest to the mass of the isotope magnesium 24. Now that makes sense because you have the most magnesium 24 in that sample. Moving on to the next one, you have the most magnesium 25. And again, you see that the mass is closest, the average is closest to the actual mass 25, okay, the one that appears most in the sample. All right, and then moving on to the last one, we see that we have the most magnesium 26. And again, the mass is closest to magnesium 26, okay, the average mass is. So however many you have, the most of, that's what's going to be closest to the average mass that's on the periodic table. So if you're just looking on the periodic table, you can learn a lot about what isotope is probably the most abundant for that element. So here, let's take the example of boron. Boron's average mass on the table is 10.811. All right, this means that there's probably a lot more of boron 11 isotope than boron 10 isotope. And then when you actually do the data, you see that there is more boron 11 than there is boron 10. Okay, so whatever the mass on the table is closest to is the isotope that there's more of. All right, now let's look at how to actually calculate average atomic mass. So the first thing you want to do is take all your percent abundances and change them to decimal form. So you're going to be dividing by 100 or moving your decimal 2 places to the left. Then you're going to multiply that decimal percentage by the mass of each individual isotope, and then you're going to add all those numbers together. Okay, and that's all you got to do. So now let's look at a little example. Okay, let's make sure. All right, so we have isotope 16, which has this percentage. We have isotope 17, which has that percentage, and we have isotope 18, which has that percentage. So the first thing we want to do is get all those percentages into decimal form. Okay, so let's make sure I've got my little smart ink going here. All right, so we get 0.9976, and that's for isotope with a mass of just 16. Then we have 0.04, so that's going to be 0.0004 times the isotope 17, and then we have 0.0020 times the isotope 18. All right, so this gives us 15. Woo, look at that pen. It's doing some good stuff. All right, and then the next one. we get 0.0068, and then 0.0020 times 18 is 0.036. Okay, now you got to add all those numbers up. So we got 15.9616 plus 0.0068 plus 0.036. So that gives us 16.0044. All right, and that is the average atomic mass for oxygen based on those percentages, and that's how you would do it.